Okay, so the next thing we should talk about is the continuity of functions. This is something more than having a limit at a point, uh, and it's actually something less than having derivative. It is somewhere in between having limit and derivative, but we will see these things more detail when the derivative stuff comes. First of all, what does continuity mean? So here is the definition of continuity. Actually, I have talked about this in one of the previous videos, as actually in the limits videos. So there, remember, if the limit is equal to the definition of the function, then it's called continuous at that number. So it is nothing but that. A function f is continuous at a number a. So this time a must be in the domain. So we also care what happens at a. In the limit we don't care, but in the continuity we care. So if the limit of the function when x goes to a is equal to what f of a is equal to, okay, so if f of a is equal to the limit of the function, then the function is called continuous. Uh, so let's see this with a graph. Let's say we have y-x, and let's say this is the graph of a function. Let's say this is a, and this is the function f, and here this is where f of a is. As you see, the limit as x goes to a of this function is exactly equal to f of a. So if the limit and the definition of the function are equal to each other, then we say f is continuous at a. Okay. Um, well, if f is not continuous at x equals a, then we say f is discontinuous at a, which can also happen. Okay. So, for instance, some examples. Let's say we have something like this. Let's say this is all happening at 4. This is 1. Let's say this is 3. And let's say this is, let's say, minus 2. Then what can we say? This is f of x. The limit from the left of 4 of the function is equal to 3, right? Because the output values from the left of 3 is approaching to 3. But this is not equal to what f of 4 is, which is 1. As you see, f of 4 is defined as 1. They are not equal. But that's also not equal to the limit as x goes to 4 from the right, which is equal to minus 2. So none of these numbers are same. So then we say f is discontinuous at x equals 4. But look at the other places. We can look at, for instance, let's say 5. Let's say here is 5. It's continuous, everything is equal. Left limit, right limit, definition, they are all equal. So f is continuous at x equals 5. And let's say this number is minus 1, because at that point, the limit from the left, from the right, are all equal to minus 1, which is f of 5. Okay. Um, so we can see so many examples about this, but I'm going to talk about types of discontinuities. Like, so let me mention that. Types of discontinuities. So one of them is something like removable discontinuity. So I should say type 1 removable discontinuity. So like, for instance, if we have something like this, we have something like this. Okay, let's say this is x squared minus 1 over x minus 1, and at 1 it's undefined, but the limit is 2. Okay, because if you look at the limit of this thing as x goes to 1, actually you can factor x squared minus 1 as x minus 1 times x plus 1, and then simplify with x minus 1, 1, 1 here. So you have limit x goes to 1 of the function x plus 1, and that's equal to 1 plus 1, 2. So the limit exists. However, f of 1 is not defined. So if we define f of 1 to be equal to this limit, which is 2, then we can make this continuous, which this 2 comes from the limit of the function. Then f will be continuous. So if we can make a function continuous just by a definition like this, then this is called a removable discontinuity. Actually, it's discontinuous because f isn't even defined at 1, but we can define f of 1 to be equal to 2. Okay, so if we define f of 1 as equal to 2, then it's going to be equal to the limit of the function also, and we are going to have a continuous function. So this is called a removable uh, discontinuity. So if there is a hole in the graph, then it's a removable discontinuity. The second type is infinite discontinuity. So this is something like if we have an infinite limit, let's say something like this, and then the function is defined like this here. Let's say this is 2, this is 0 here. So if we have limit x goes to some number, let's say in our case 0, is equal to plus infinity. In our case, it's plus infinity, but it can be also a case like minus infinity. Well, then it doesn't matter what f of 0 is, right? It doesn't matter what f of 0 is, because it's going to be some finite number, let's say, but a finite number and an infinite limit never will be equal, so there is no way to fix this discontinuity. So there is no way to make this a continuous function. So this type is called infinite discontinuity. If the limit from the left and right is some infinity, then it's called infinite discontinuity. The third type is like the step functions or the heaviside step function. That's jump discontinuity. Well, again, there is no way to fix these ones either. So, well, we are going to have things like these. Let's say we have some function like this, the heaviside step function. Okay. So this is 1, this is 0. And it's going to look like this. Okay. There is no way to fix this either. Okay. So a jump discontinuity is something like from the left, the function has a limit which is not equal to the limit from the right. So this is called a jump discontinuity. Again, it doesn't matter what the definition of the function is. Okay, it's a jump discontinuity. So you can think about more wilder ones, like like something like this, and then something like this. This is also a jump discontinuity. Or you can have jump discontinuities like this. Okay, this is also a jump discontinuity. Everything is different. Definition different, left limit different, right limit different. Okay, these are jump discontinuities. Okay. There is also left continuity and right continuity. So let me write that definition as well. Sometimes we will deal with that too. For instance, functions like square root of x is going to be right continuous from 0. I mean, at 0. So a function f uh, is continuous from the right when if the definition is equal to the right limit. So the right limit is a upper plus, and similarly a function is called continuous from the left if the left limit and the definition are same. So if the limit from the left is equal to the definition, then it's called continuous from the left. Okay, so this is something like this. Let's say this is a. The right limit and the definition are same, but this one is something like this. The left limit and the definition same. To give this as another example, like square root of x function. Square root of x function. This is continuous, right continuous at 0. Square root of x function. For a left continuous function, we can think about square root of minus x function. This is left continuous. It's not defined from the right of 0. Okay, so this is a left continuous, right continuous, left continuous. Okay, well, another thing which we will talk about quite often is continuities or interval. So a function f is said to be continuous on an interval if it is continuous at every number in the interval. Okay. Um, Okay, so another thing is we can't have combinations of continuous functions to have new continuous functions. So, well, actually, this is not a definition. This is actually a fact. So I should rather say theorem. So theorem means a fact which you can prove. Okay, theorem means a fact which one can prove. So this fact is if we have two continuous functions, f and g, let's say at some point a, and let's say c is a constant number, okay, then the following functions which we will get from the combinations of these f and g and constant c will be also continuous at the point a. So what are these functions? 1 f plus g, 2 f minus g, 3 constant times f, 4 f times g, 5 f over g, but we don't want g to be 0, otherwise it's going to be undefined. So if g is 0, f of g will be undefined, then we cannot talk about continuity, because undefined means f of g is not defined when that g gets 0. So we don't want to be 0. We don't want, okay, I should be more careful here. G of a, we don't want it to be 0. Okay, these are very easy to see. So, but there is another theorem which is going to be quite useful most of the time. Any polynomial is continuous everywhere. Okay, so what is a polynomial? A polynomial is a function like an x to the n plus an minus 1 x to the n minus 1 plus dot 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 a2x squared plus a1x plus a0. For instance, we can have something like 3x to the fifth minus 4x to the 4x cubed plus 7x squared minus 6x minus 1. This is a polynomial. Okay, x squared just it alone is a polynomial. Linear functions, polynomial. Constant functions, also polynomial. And they are continuous everywhere. Why? Because whatever point you choose, the limit and the definition of the function at that point will be same. So you can try this, and it's always true. This is the first part. And the second part of the theorem is any rational function. Any rational function, remember, a polynomial over a polynomial. P of x over q of x. P, q, both polynomials is continuous whenever or wherever it's defined. So that means it will be defined whenever q is non-zero. So that means q of x, whenever this is non-zero, it's going to be defined. So it's going to be continuous everywhere when q is non-zero. Okay, so these are going to be very useful facts. But a more general fact, which I should maybe say, is all of the following types of functions are continuous at every number in their domains. Now remember the domain business, we were talking about domain. So as you see, domain is kind of important to know. Okay, once you know the domain of a function, as you can see, you can talk about continuity of such a function, because these functions are A, polynomials. So we have given some example above. B, rational functions. Maybe I should just write it the other way, like so polynomials, let's say x cubed minus 5x squared plus 7x plus 4. This is a polynomial and it's continuous everywhere. B, its domain is all numbers, so it's continuous everywhere. Since the domain of polynomials is everywhere, it's continuous everywhere. The rational function, so this is something like x plus 1 over a polynomial over a polynomial, x squared minus 3x plus 5, okay? Again, this is continuous everywhere on the domain. As long as the bottom function is never 0, it's going to be defined and it's going to be continuous. Or root functions, as long as they are defined, so like square root of x or cubic root of x squared. These are going to be, well, the first one, it's defined, its domain is positive numbers and 0. So there, it's going to be continuous. The second one, well, it's defined everywhere and it's continuous everywhere. The trigonometric functions, so these are sine, cosine, tangent, secant, and there are also cotangent and cosecant, so etc. Okay. Their inverse also, E, inverse trigonometric functions, in their domains, they are continuous. Okay, so we can talk about 6 inverse trigonometric functions here. And then exponential functions. These are also continuous everywhere. So like 2 to the x, e to the x, 3 to the x, 10 to the x, okay? And the last one are the logarithm functions. Logarithmic functions, so like log 2 of x, ln of x, log 3 of x, etc. These are all continuous functions. And you can also remember their domain, their graph, so you can know where they are continuous. Okay, another theorem, another fact is if f is continuous at b, x equals b, and limit x goes to a of f of g of x is equal to f of p, well, okay, I rushed this a little bit. So, okay, if f is continuous at x equals b and limit x goes to a of g is equal to b, then limit of f of g of x when x goes to a is equal to f of b. Or to write this thing in a nicer way, so limit of f of g of x is equal to f of limit of g of x. Okay, so this is something nice. You may think, hey, where did this come from? But it is actually something nice. Let me show you an example. Let's say find limit x goes to 1 of arc sine 1 minus square root of x over 1 minus. Okay, I'm going to make this a little bit something easier. I say x goes to 0, something like this. Well, you can just take the limit inside the arc sine. X goes to 0, 1 minus square root of x over 1 minus x. And then take the limit inside, which is going to be 1 minus square root of 0 over 1 minus 0. This is arc sine of 1 over 1, which is 1. Well, which angle gives you 1 when you take the sine? That's pi over 2, right? Sine of pi over 2, since sine of pi over 2 is equal to 1, arc sine of 1 is pi over 2. Okay, as you see, we can just carry the limit inside that function. Otherwise, what are we going to do with that? There is nothing we can do. So, another fact is if we have two continuous functions, then their composition is also continuous. If f and g are continuous, then f of g is also continuous at, well, of course, I need to say here f is continuous at a and g is continuous at f of a, then f of g is continuous at a. So I should rather say this. F and g are continuous at a and f of a respectively, then f condition g is continuous at a. Okay. There might be some nice applications of this last theorem. For instance, let's say we have okay, I want to say it with a different letter. So let's say h of x equals cosine of x squared. So if we say f of x equals x squared and g of x equals cosine of x, well, both are continuous functions. Remember the earlier theorem, both continuous functions, so their composition also continuous. Also continuous. And then there is one last thing, intermediate value theorem. This may have some nice applications again. You may have heard about this. Intermediate value theorem. I'm going to show what it means after I say what this is. It says that suppose or assume that f is continuous on closed interval A to B. So A and B are included. And then let n be a number in between f of A and f of B, let's say. Okay? Or maybe it is something like, maybe f of B is smaller. That's a possibility. F of A is bigger. In any event, n is a number between f of A and f of B. Then there exists a number C in the open interval where A and B are not included, such that or so that f of C is equal to n. Now, okay, this may seem confusing, but let me draw a picture here, and then you will see what I'm talking about. Okay, so this is x, this is y, and then let's say this is A, let's say this is B. So this is where f of A is, and this is where f of B is, right? So if n is somewhere in between here, then this theorem saying like here f is continuous on the closed interval A to B, and then if n is between f of A and f of B, then there must be some number C in the interval A to B. Okay, so this is what this theorem is saying. But let me show you an application of this. This is an example. Show that the equation x cubed minus 7x plus 1 equals 0 has a solution. Okay, what does this mean? Now, what is solution? Solution means when you put that solution into the equation, that solution makes also the left-hand side 0. So you have a 0 equals 0, which is an equation. So that is called a solution. If there is a number like that, it is called a solution. So how do we show such a thing? So just say f equals x cubed minus 7x plus 1. Okay. So what I'm going to try to do here is solution means this function x cubed minus 7x plus 1, it's going to be a function like this. It's a polynomial, third degree polynomial. It's going to look like something like this. So this point here is a solution. If I can find a number like that, it's a solution. Now, this is not asking me what the solution is. It is asking me whether there is a solution or not. So how do I show there is a solution? Okay, I'm going to find an interval. Okay, so this interval here, let's say call this C, call this D. If I can find something like f of C, which is on the negative side, and then if I can find some D where f of D is on the positive side, then there must be some number in between where it's going to be f of A is 0, and then I'm going to find that, right? So, okay, maybe I should use my earlier letters because I want to stick to my use of letters. So this is A, B, B. So this is B. And I'm looking for a point like C. Okay, so let's say A is equal to 0. So first I want to find some number where I get some negative number. 0 cubed minus 7 times 0 plus 1. Okay, this is plus 1. This is something positive. Okay. Maybe this is not what I want, but okay, I can try maybe something else. Or let me try this function to minus 1 here, so because I don't want to go too complicated anyway, I can still do it, but I don't want to waste too much time. So let's say this is minus 1, this is minus 1, this is minus 1. Then what we are going to find is a minus value for f, right? Now, if I can find a second number where f is going to take a positive number, so, okay, let's change this to minus 7x to plus 7x. Okay, so let's make this plus. Okay, so x cubed plus 7x minus 1 has a solution. Okay, now let's try b equals 1. What is f of 1 going to be? 1 cubed plus 7 times 1 minus 1. What's going to happen here? 8 minus 1 plus 7. So, okay, let's try sketching what's going on here. 0 is mapped to minus 1. 1 is mapped to plus 7. Okay. So then this means the function is a continuous function. By the way, x cubed plus 7x minus 1 is a polynomial, so it's continuous everywhere. It's a polynomial, so it's continuous everywhere, also on the interval 0 to 1. That means it's gonna go continuously from this point to the second point. So it's gonna have to do something like this. I don't know what it does, but I know it has to go from this point 0 to minus 1 to the second point 1 to 7 continuously without any jump. So it must then intersect the x-axis somewhere. Let's say this number is c. Since f is continuous, it must change from negative to positive somewhere in between, which is, let's say, at c. From negative to positive, well, negative is, 0 and minus 1 point, to positive 1 and 7 plus 7. Somewhere in between, at some point in the interval 0 to 1. Okay, I should say open interval. Let's say that point is c. Okay, so then f of c will be 0. So it must come from negative to positive, and it must be 0 somewhere. Okay, because that point is c0 point. So you cannot switch from negative to positive. I mean, if the function is continuous, you cannot jump from negative to positive. You must be 0 somewhere in between, and there must be a point where the function gets 0, and that 0 is a solution. Okay, so that 0 is a solution. So f of c equals 0 means, it must get 0 somewhere. So c, f of c means c cubed plus 7c minus 1 equals 0. So c is a solution for the equation. Okay, and this is called the intermediate value theorem. It has so many applications. Like if you have a continuous function, then the function takes all the values between f of a and f of b. This is saying that, but you can use it for a question like this. Okay, And you may actually be dealing with equations like this in your future programs, future courses, classes, or maybe even in real life. And you may be wondering if there is a solution for the equation, or if there is a value which which the function you are dealing with has to take or not. So this is about that. Okay.